It's recording now. Perfect. Okay, great. So our final talk of the workshop today is going to be from Antonio Vergari, who is a lecturer in the machine learning in the Department of Informatics at the University of Edinburgh. He's going to be telling us about the Unifying reasoning framework with Trustworthy AI. Thank you, Antonio.
All right, thank you. Thank you for the introduction, for the invitation. I'm very keen on connecting with all of you here. So I do research in probabilistic machine learning and AI with a special focus on designing and learning models that conform to our expectations. This is why I label this under Trustworthy AI or machine learning. And in this talk, I'm not gonna present you a single work, but can you hear me? I still...
No,
I think we could make it out.
You're very quiet. We have a small speaker in the corner of the room. Turn the AC off.
If you're saying something, it's not super clear what you are saying. Can you hear me?
It should be better now, I think.
Okay.
We turned the AC off.
Okay. All right. Can you hear me?
Yeah, we can hear you. I think otherwise we can try again this speaker.
Okay. All right. So I'm not going to show you a single work, but a collection of my works trying to build up a single framework for reliable probabilistic reasoning, essentially. So if I have to summarize my old research in a single tweet, this will be the single tweet. And this is also the outline for the talk of today. I would really like to understand when and how we can perform probabilistic reasoning efficiently and reliably. And these are the desiderata for Trustworthy AI. So when I say probabilistic reasoning, what I mean essentially is just like computing certain mathematical expressions over the probability distributions that are encoded in our models. So which kind of mathematical expressions? Well, you might have seen them every day in machine learning and AI. So I'm going to give you some examples now, but let me just state that just to be compact, I'm going to call them queries from now on. So whenever you hear query, you can just think of some complex quantity over a probability distribution. For example, you have a model, you can have even a probabilistic model, and you do not observe some values because they are missing. So you want to marginalize them out. We call this a marginal query. Your model could be a classifier. So you might be interested into predicting the mode of a probability distribution. So for example, what's the most likely configuration for your set of labels, given your input variables? And we call this maximum a posteriori queries, map queries. Or you can have mixed queries. You can have marginal and map queries all together, doing predictions while you have missing values. Or at the sometimes you can have a machine learning system when you have multiple models, right? And you want to understand when these models are somehow different. So you might want to compute a divergence, for example, a Kullback-Leibler divergence between two distributions. Some other time, you might want to compute some more involved queries like expectations. For example, if you have to deal with missing values with your classifiers and you don't want to impute them, you might want to compute the expected output of your classifier, that is sort of averaging over all possible missing values. Or if you really are keen into having a robust model that is trustworthy, so you would like to be to defend yourself against adversarial adversarial attacks. So to do that, one technique is the so-called smoothing. So you can have like this randomized smoothing that essentially it boils down to this expression here, computing the expectation of your classifier F over all possible additive noise E. You add this noise E and you assume this E comes from some simple distribution, let's say Gaussian. I will be zoom in this specific query later on, but just what I want to give you here as an impression is that you have all these kind of queries and they share some commonalities, right? There are lots of expectations in between them. So my question for you is, if you are a machine learner and you might face computing one of these queries in your daily life, how would you essentially solve this? How would you compute these quantities, these mathematical expressions? Do you have any ideas? Feel free to speak or unmute yourself. No clear idea. Okay. All right. So I will try to answer for you. So whenever we see those expectations, generally, the simplest thing that comes to mind is essentially to do sampling, right? To do a Monte Carlo estimate of those expectations. And if you do that, you can somehow approximate all those computations somehow. But this is very unsatisfactory, moreover, for a point of view of trustworthy systems. Why is that the case? So first of all, these models are not efficient. I mean, whenever we have to do a Monte Carlo estimate, we need lots and lots of samples to try to approximate well those integrals, and we have no guarantee. So we just have these asymptotic guarantees, and this is really, really not reliable. But when it comes to efficiency, let me make the statement even more clearly by perhaps a concrete case. So back to this smoothing query for adversarial robustness. Again, you want to synthesize this new classifier G from your original classifier F by just essentially computing this expectation over all possible noise that you can add to your single input X. So this is like a general technique to certify that you're never going to have an adversarial example in a certain bowl centered around your sample X. And you have to solve essentially this expectation for every possible input X, right? So what happens if you want to do this via Monte Carlo? Now, imagine that your F is a neural net, right? And you want to certify your single input, perhaps one image. And then to have a certain kind of, I don't know if you can see the picture. Let me move this around a bit. If you really want to get a reliable estimate, let's say a 99.99% confidence that you are covering that expectation, then no matter if you have a convolutional neural net, less parameters than the normal feed-forward neural net, you need lots and lots of time to certify a single sample. Why is that the case? Because you need millions of samples to pass through your neural net to get your Monte Carlo estimate. Now, my point is that you can reach 100% confidence and reliability with a single pass of your neural net if you impose some structure on the neural net. Therefore, you can have a trustworthy model. I'm going to show you later how to do this, but I just want to make a point here that we really want models that can ensure to compute those queries exactly. And sometimes this exactly doesn't mean that you have to wait more time. It's the opposite. You're going to be even much faster than the approximations. Okay. As I said before, we also want to be reliable. We want to have, if we cannot compute things exactly, we want to have bounds over these quantities, because whenever we are going to deploy our models in the real world, and we want to make sure that they conform to our expectations, we have to compute these queries. And we cannot really compute a bound over the result of the query. We will never know what the model is really doing. Okay, so we need these two ingredients, efficiency and reliability. So for the rest of the talk, I'm gonna use these two quantities instead of the two above. So for efficiency, I'm gonna settle for polynomial time. So no worries, it's not like generic polynomial. In this case, for all the models I'm gonna show you, it's gonna be linear in the size of the model. And for reliability, I'm going to go for the highest form of reliability, exactness of the results, which means essentially the error is going to be 0, right? So if I put these two ingredients together, polytime and exactly, this is how I'm going to shrink my initial tweet and our essentially plan for today. Let's try to understand when and how we can compute queries tractably. So tractability is the key for a trustworthy machine learning and AI. All right, just to give you a very quick recap of what does tractability mean, let me show you this pictorial depiction of many models you might know. So you had Andrea before talking about GANs and VAEs, for example, right? And this can be all kinds of probabilistic models that they encode the distribution, right? So for GANs, they might encode the distributions, but we don't even know what's their distribution. So they have an implicit distribution, right? So if we zoom in and we look at models with an explicit distribution, perhaps defined by explicit density, perhaps we have VAEs, energy-based models, and macro random fields, old school things, so on and so forth. But all of them cannot have like an exact density, for example. And if we zoom in even more and we look at models with an exact likelihood, we can have normalizing flows, classical Bayesian networks. And these models, however, cannot allow you to compute some other queries exactly. For example, marginals. For marginals, you need, let's say, some more restrictions. For example, you can compute marginals with Gaussian mixture models, with HMMs, but with them, you cannot compute maximum a posteriori queries, which are the modes of the distributions. You can do that for other model classes, and so on and so forth. You can keep adding a new query class, and in a sense, you're going to rule out parts of the models out that you have out there. So my whole point with this slide, and this depiction here, is that tractability is a spectrum. It's not a universal property, right? So there are some model classes that are going to support solving some query classes in polynomial time and exactly. So it's very tempting to rule something out, but it's even more important for me to understand the spectrum and navigate the spectrum. Now, if we have to navigate the spectrum, we can characterize, in a sense, this tractability spectrum in the simplest way possible. It's what I call a model-centric characterization. So we can have a two-dimensional table, and we can put as the column all the possible queries, all the possible mathematical expression you want to compute reliably, right? For example, marginals, marginal map, and so on and so forth. And on the rows, you can have put all the model classes that I showed you before. And so essentially, you go there and you put a check mark whenever the model class supports the query class in polynomial time and exactly, right? And you can do this. But there is an issue with this representation. And the issue is that you're going to always find new model classes, and you're always going to find new query classes. So how do we deal with this? Can we somehow try to automate this or understand this table, which otherwise is going to be infinite, have an infinite number of columns and an infinite number of rows? Okay, so here is what I'm proposing. I'm proposing you 3 different ways to understand, to navigate this spectrum. The first one I will call is sort of like computer science or theoretician perspective, right? So we would like to understand that for a given model class, if a query class is tractable or not, right? The second one, it's the classical machine learning perspective. So we really are in love with the task we want to solve. So we start from the query, and then we look at, is there a tractable model class that is expressive enough, but at a certain time also reliable, right? I'm going to give you the third later on, but let me focus here on this machine learning perspective, which can be the one that perhaps it's more convenient for us. So here is the big question from this second perspective. So given a class of queries, or if you want tasks in machine learning, can we somehow automatically find a class of expressive models that is still tractable for that gives us these reliability properties? And for model classes, I'm going to focus on class of deep computational graphs. And you're going to see how these are linked to tensor factorizations and representations in a bit, if we stick with me. So I'm going to start building these computational graphs from examples that you already know. For example, Gaussian mixture models. So for a Gaussian mixture model, you just put in a convex combination some Gaussians, right? And you get a model that is more expressive than every single Gaussian. For example, this bimodal distribution here in orange, right? Now, how can I represent a GMM, a Gaussian mixture model, as a computational graph? Well, the recipe is here in the mathematical formula. So whatever I need to do is to introduce, for example, 2 computational units in my computational graph. And these are going to compute the densities, the PDFs of the 2 Gaussians, right? And these are 2 different Gaussians, everyone with its own mean and standard deviation. And they are Gaussians over the same variable, over the same sample space, let's say for feature X1. Then I'm going to introduce a sum unit that's just going to perform essentially the weighted average of the PDFs here. So for every input, the output of this subunit is going to be essentially the PDF according to the Gaussian mixture model, right? Quite simple. So for example, just to make it very, very concrete, if I observe a value 1 for the feature x1, then I'm going to feed that to the first Gaussian unit. The PDF is going to be 0.06. The second Gaussian unit is going to output a different PDF because it has a different kinds of parameters. Then I'm going to do the complex combination, and the output, the joint PDF, is going to be 0.09, right? So inference in a probabilistic model is going to get mapped to a feed-forward evaluation of this computational graph. And this is a simple case from a Gaussian mixture model. Now, let's make things a little bit spicier. And now let's use two variables. Let's say x1 and x2. And these can even be like sets of variables, actually, right? So I can represent a multivariate Gaussian by a vector for the mean and by a covariance matrix, right? And for these covariance matrices, I'm highlighting in colors whatever is non-zero. So you can see that there are two groups of variables, the blue and the red, and the yellow and the green, that are independent. And therefore, if I want to write now the joint PDF of this Gaussian mixture model, when these are essentially the two covariances of the two mixture components, what I need to do here is essentially just do the product of the small Gaussian defined by this covariance blue here and the red one. And on the other components, the yellow and the green, right? So these are essentially some local factorizations. If I need to translate them as computational graphs, then as before, I'm going to have like these inputs that are multivariate Gaussian PDFs in this case, but I need to introduce a third kind of unit, the product. So I'm going to take the product of these PDFs here, the product of these other PDFs here, and then putting them together with a sum to yield the inference pass of a Gaussian mixture model, in this case, which is multivariate with a certain factorization of their covariance matrices, right? So three kinds of units so far. So by this recipe, perhaps you can already see how you can translate other common probabilistic graphical models that you might know from your machine learning and AI classes, like HMMs, hidden Markov models, in the same way here. So you're going to have like a latent state that, if you know HMMs, this is essentially encodes a mixture model. And therefore, you can just encode that as a sum unit, and then you're going to introduce the products as needed to represent the factors in the HMM. Now, all of this coming from this example is to build a grammar. And this is a grammar of tractable computational graphs. We call these probabilistic circuits or shorthand PCs. And you've already seen that, right? I already give you all the interesting ingredients, but let me state this again. Let me give you again a recursive definition of this grammar to try to build a little bit more intuition. So whenever we have a very simple function, we can call that a circuit, and we can represent that as a very small input unit here. For example, the PDF of a Gaussian, but it could also be the probability mass of a simple distribution, or it can be a joint probability mass and density, right? Then we have a second kind of unit, the sum unit, and then we can have a weighted sum of other circuits, and that's going to be a circuit. Third, we can also have a product of circuit, and that's going to be a circuit. These are the three ingredients you need to know. And once you know them, you're allowed to compose more interesting circuits and more deeper and deeper circuits of this kind. All right. So before taking questions up to this part, let me show you again how you're going to evaluate a circuit. So for example, I want to compute the simplest query possible. Like, you know, in this case, I have a joint distribution over 4 variables, x1, x2, x3, x4. And I know that the distribution is encoded by the circuit here. Now I want to understand how to compute this in practice, right? And again, this is going to be just a feed-forward evaluation of the circuit. So it's just going to take linear time in the size of the circuit. So how do we do this? Well, again, for the values of the variables that I observed, we just feed that to the input units, and the input units are simple distributions. Let's say they are Gaussians. You evaluate the PDF there. You're going to collect some values, and then you keep propagating the values feed forward by computing sum and products and sum and products until you reach the last unit, the last computational unit, and you read out the value there. So this is going to be the answer to your probabilistic query, and it's going to be an exact answer. Is it clear so far? So please, this is perhaps a very good time to ask questions about how these computational graphs work, if you have questions. I'm not able to look at the chat, so perhaps let me see. There is a loop, feedback loop. Was someone about to say something?
There are no questions in the chat.
Okay.
So everything
All right.
looks good.
All right. Okay, I'm assuming I'm doing a good job, or you're thinking already about lunch. Okay, so well, why are these computational graphs very appealing? First of all, they are very expressive because they have all these intermediate mixture models, and they actually realize of hierarchical mixture models. You might have already seen that these are some kind of polynomials defined over the input functionals. And they also provide a grammar for express many other models. And this is why I found this very, very unique and appealing. So for example, many of you might have understood that these are some sort of like general way to define very sparse tensor factorizations. You can understand this by looking at classical tensor factorizations like Tucker, for example, or hierarchical Tucker, or the canonical polyalbic decomposition, and write them down as very simple circuits that are shallow circuits. They are not very deep. You can also extend like classical hierarchical tensor factorizations into the language of circuits. So circuits are a sort of like more general language when you actually map inference to this bare-born computation of neural networks and computational graphs. I showed you before how you can turn an Edinburgh model as in general any bounded tree with PGM into a circuit. You can, of course, do matrix and tensor factorizations. And even more interesting, you can do old school machine learning system models like decision trees, decision forest, XGBoost. They are always all a special case of PCs. And of course, there is a new generation of probabilistic models that have very different syntaxes, but under the hood, they are simply PCs. You can always map them into the language that I showed you so far. So they are expressive models. I'm going to give you some concrete examples later, why they are and how they compare to other deep generative models. You have a single grammar to represent many model classes, but what's really key for my presentation and what my interest for Trustworthy AI is that certain structural properties over these computational graphs essentially correspond, sometimes in a one-to-one mapping, to tractability over query classes. So what it means is that you can certify that a model represented as a circuit supports the exact computation of certain query classes just by looking at structural properties over its computational graph. Just to give you some example, there are lots of properties. I just mentioned 4 here. They have strange names for you. For example, smoothness, decomposability, determinism, and compatibility. They generally do not mean what you think they mean. So let me give you one example. So for example, a decomposable circuit is a circuit where every product node receives inputs from sub-circuits defined over disjoint sets of variables, like in this case here. So essentially, every product node defines only a local factorization. On the other end, we say that the circuit is smooth if every sum unit, every sum node in the computational graph receives inputs exactly from functions defined over the same scope. And this makes sense because a sum unit defines a mixture model. And you always sum, let's say, Gaussians, for example, that are defined over the same sets of variables. Otherwise, it wouldn't make that much sense. Now, I'm not going into detail for the other properties, but I'm going to tell you what you're going to get if you just make sure that your circuit is smooth and decomposable. You're going to get a super interesting property, which essentially is that you can compute exactly in a single feed-forward pass every possible integral over any arbitrary subsets of the input variables. So for example, you can compute the partition function by marginalizing over all the variables, but you can compute every exact marginal for every possible subset. So you can always compute exactly, you can always marginalize out exactly missing values. This is a remarkable property, and I can prove that this like sufficient and necessary condition to do that is that the circuit needs to be smooth and decomposable. Now, how does it work again? So suppose that you have the same circuit as before, but now you want to compute the marginal density over only two variables, x1 and x4. You just feed those values to the input units that were defined over x1 and x4, and you marginalize the other out. So the other are going to be, in our previous example, simple Gaussians. So if you marginalize them out, they're going to output 1, right? Integrate over all the domain. And then you just keep propagating the values as before. And the result is ensured to be the exact computation of the two-dimensional integral shown here in the example. Okay, so these circuits are able to represent many models, so they are very interesting. So what do they get us? So we can move from this model-centric characterization tractability as before, when we have all these models and all these query classes, and instead have a single formalism that represents many of the models, many of the rows, but now the number is bounded. It's not a model class, but it's a property of the computational graphs. So you can say, for example, that if you have smoothness and decomposability, the first two rows here, then you can ensure that you can compute tractably marginal queries, conditional queries, and all moments of the distribution. So now we have a property-centric theory of tractability. And this is one first revolution with respect to whatever we were able to represent before. I'm going to give you a second step later on. Okay, but I might hear a little bit of skepticism, like you can say like, yeah, it's just sum and products, right? How good can this model be, and shall we really use them? Why not shall we use a VAE, for example, right? Well, first of all, let me ensure that these models are very accurate generative models. And if you have to measure models in terms of the likelihood, or if you want bits per dimensions, PCs are very competitive. And sometimes on simple data sets like MNIST, fashion MNIST, EMNIST, and so on and so forth, all these variants of MNIST, PCs, in this case, indicated by this column here, this HCLT, not going into detail how this PC is learned from data, but this yields the best bits per dimensions, which you can think of like a renormalization of the log likelihood. And you compare this against other kinds of very sophisticated normalizing flows that still can get you exact likelihoods, or even variational autoencoders. And for the variational autoencoders, of course, you do not have an exact likelihood, but you have to put some lower bound for that into the play. All right, so PCs are expressive, but more importantly, they are fast and they can get you reliable approximations. So even if you want to compute an elbow because you're doing variational inference, if you restrict your computation to a variational family that is a circuit, then you can compute the elbow even exactly. A small disclaimer, whenever we compute an elbow for a VAE, for example, we cannot even compute the elbow exactly. So it's just a stochastic estimate of the elbow. And this is from a nice paper from Stefano Hermon and then Nishi from NeurIPS a couple of years ago. Number 3, because PCs can be naturally combined with general neural nets. So I've called PCs so far computational graphs, but they just are a special case of neural nets. When you impose a little bit of structure on these computational graphs, and you restrict your neurons to be the sum products and input nonlinearities. So from the point of view of tensor factorizations, or better, tensor factorizations from the point of view of deep learning have been called somehow multiplicative interactions. So this is a nice work from people at Google from this was like, I guess, iClear 2 years ago. So, and they were showing them that essentially, if you have these tensor factorizations, you can get on par with neural nets in classification cases, right? Or even better. Now, I'm going to take this idea a little bit farther and then show you that if you take a neural net that still has no linearities, but computes just these products and sum, essentially, then you can compute interesting queries exactly. And what I'm trying to do is that essentially you have this, impose a little bit more structure in this multiplicative interaction. So instead of having just a bilinear product here, as the people from the neural nets do, I'm going to have a bilinear product over functions with these joint scopes. So we call this decomposable multiplicative interaction. The other term really do not make really a difference, but the whole point here is that you're going to have this bilinear interaction, but then G is defined over a set of variables and H over a different set of variables. Now, if you just change this, you're going to obtain the result that I was talking about. So you're going to have a classifier that is as accurate as the other classifiers, but however, you can compute this expectation in a single pass. So you can certify your input, let's say one image, exactly in a fraction of the time that you will need for any other common neural nets just by computing the Monte Carlo estimates, which of course you can parallelize on the GPU, but yeah, in our case, we need to parallelize millions of samples. Okay, last but not least, I'm not going to spend much time about this, but I just want to tell you that PCs are very easy to use when you have hard constraints in your data, and you want to model hard constraints exactly because you don't want to make predictions at deployment time that go behind this constraint. So, for example, this is very much used in neurosymbolic learning and reasoning. So if your aim is to predict a path on a map, and this map is the map of Warcraft, for example, and I just give you 2 points, this top left point and bottom right point, and the neural net essentially as predict is every edge in a grid that is overlaying the map exists or not, the neural net is never going to do a good job, in the sense that the path that it's going to output are not even path, do not make sense. And essentially, they are not consistent with the implicit constraint that the configuration of edges should be a complete path in the grid. There are lots of alternatives to try to regularize this, that is, try to inject the hard constraints during training only. But you're never going to have the guarantee that at deployment time, at test time, the neural net is going to output a solution that is a configuration of the edges here that exactly conforms to your hard constraints. On the other hand, if you use circuits, you can do that, and you have 100% guarantee that the network is going to output that. I'm happy to talk about this more if you're interested. But let me just get to the last point and tell me how much time do I have left, please. I will try to be as fast as possible accordingly.
So about 5 minutes.
5 minutes, okay. All right, I will try to wrap it up in 5 minutes. So my point is that from this property-centric theory of tractability, I would like to move to a more compact representation. Why is that so? Because we can still have essentially infinite number of columns. We have lots of query classes that we were meant to solve, right? So this table is still infinite in one dimension. How do we solve this problem? Well, we need to solve this for many query classes, right? So let me recap some of them that might be interesting that I showed you at the beginning. Computing marginals, computing divergences, computing expectations, because sometimes these expectations are to ensure that our model is robust against adversarial examples, right? So what I'm going to do is that all these queries, I'm going to decompose them in a single language for queries, or as I like to call this, is a query calculus. So all the expressions that I showed you before in this talk essentially boil down to some computations of some integrals over these operations here: the sum, the product, the power, the logarithm, the exponential, and the division, right? These small colored blocks here. Now, here's the idea for getting a small breakthrough. Now, I can also represent a query, these mathematical expressions, as a small computational graph. This is actually going to be a higher order computational graph. Sometimes you're going to hear me call this pipeline. And why it's higher order? Because this is a computational graph whose intermediate outputs are going to be circuits. And the bottom line is that by doing this, what I need to do is only define what's the semantics of these small operators, these small blocks in colors here. Once I do that, I can reuse them across every possible query I want to compute. Let me give you a concrete example. So this is the classical definition of Kullback-Leibler divergence between two distributions. And here is represented as a pipeline, a higher order computational graph over circuit below. Let me unpack that for you. So first of all, there is a division operator, right? So I'm assuming here that your input model, the P and Q, can be represented as small circuits. Now, imagine that I can do the division, the quotient operator, and I can represent the result as an intermediate circuit R, another model defined in the same language of the sum, products, and input units. Then I'm going to pass R through the logarithm operator, and I'm going to have an intermediate result S, yet another circuit. Now, what I need to do is essentially to do the products of the circuit for P and the circuit for S. If this is another circuit T, whatever I need to do is essentially just do the integration over this circuit T, right? And this is how we're going to compute the Kullback-Leibler divergence. Very similarly, I can compute the cross entropy between two distributions, or another expectations for the moments by computing the powers, and so on and so forth. Now, I only need to define the semantics of these small blocks. So for example, for the logarithm, the semantics is defined in terms of the structural properties of the inputs and the output. So I can ensure that if the input circuit for a logarithm block is a smooth, decomposable, and deterministic, where deterministic is yet another structural property I didn't have time to talk about, then I can prove you that the output is going to be a compact circuit, what size is going to be polynomial with respect to the size of the input, that is still smooth and decomposable. So essentially, I'm building a typed language over small query operations. Now, for the products is something analogous. You just want an additional property called compatibility. But my point is that we're going to move from just a property centric characterization over where columns were query classes to a much smaller table when I just need to map the structural properties of the inputs with essentially the unitary operations you can find inside the queries, like the sum, the products, the powers to the natural, power to a real, so on and so forth. So what I'm doing is that building an atlas of composable, tractable atomic operations. Now, back to our original question, given a class of queries, can we automatically find an expressive model class that is tractable for it? And the answer is yes. Implicitly, I just showed you how to do that. I'm going to do this example in reverse for this cross entropy query. Now, what the point is that we can simply do this by reasoning backwards, right? If we have this plan for the query, this higher order computational graph, I know that the circuit S needs to be smooth and decomposable if I want to compute the integration exactly. Then I can reason backward and say, okay, if I need the output S that is smooth and decomposable, what are the properties of P and R? They need to be compatible. And the same I can do for the logarithm. What's the additional property that I need for the logarithm such that R is smooth and decomposable? I need Q to be deterministic. I can put all the pieces together and I exactly know what are the structural properties of a P and Q that ensure that S is smooth and decomposable. I also can prove you that if some of these structural properties are not satisfied, some of these divergences become intractable. But what's important in this case is that just by defining these small blocks, for example, you have access to tractable versions of all these information theoretic divergences and queries. Okay, then ultimately, can we essentially just given a model, a query class, put up an efficient algorithm that's gonna compute that? And yes, we can somehow automagically distill that. And the answer is essentially in the pipeline that I already showed you. So instead of drawing them with fancy colors on a slide, we just map them to constructs in a programming language, for example, functions in Julia. And this is how you can build your alpha divergence with 4 lines of code, just by composing these circuits together. Okay, I'm reaching the conclusions here. I hope I was in time still. So the bottom line is that if we want reliable machine learning models, at a certain point, you need to answer many queries. Queries to make sure that the models are fair, involving certain kinds of expectations, queries to make sure that the models are robust, involving other kinds of expectations. Now, you can automate the construction of reliable models by using a single model class, that of these tractable computational graphs. And you can do this even by considering that the queries as higher order computational graphs that operate on this unified representation. And if you're able to do that, you can map that efficiently to code. And you can have models that output what's behavior. You can always inspect by composing these small blocks together, by inspecting their behavior, expected behavior when you have missing outputs, expected behavior when you condition protected attributes, expected behavior when they receive an input you need to certify for adversarial robustness. That's the end of my talk, I guess. So I can talk a little bit more about like how to approximate and whatever happens, but I would like to spend perhaps the last 20 seconds just to talk about something totally different in this case. So a couple of days ago, we realized that unfortunately, rights are really not forever, and we need to fight for them every time, right? And they're really not granted, even if we think of them as something that is for granted. So this happened in the US. I was there for 2.5 years, and we thought that at a certain point, everything is going to be better with Biden. But actually no, right? But we don't really need also to look at the US to be a little bit scared. So if we think about the constitutional right for abortion that is no more in the US, and the equivalent that we have in Italy. So in Italy, we have like the so-called Legge 194, that should essentially give Italian women the same thing, which, however, is never enforced 100% of the time. Most of the time, it's totally ignored. So it's incredible how many of the times, essentially all the physicians, the gynecologists are conscientious objectors and just say, I cannot do this. Even if it's by law, there is my conscience that tells me that we cannot do this. And this, in some areas, has some percentages that are really crazy. So in practice, what happens is that we do not have the right for abortion even in Italy. So what to do now? So the first thing should be essentially just inform ourselves and try to spend a little bit of time, perhaps outside machine learning, to try to understand which rights do we have essentially, and which are really given for granted, which are true in practice, and what we can do to change things. Yeah, it's a matter of praxis, essentially. All right, thanks. I'm happy to take questions.
Anyone from the room is on mute. Can you hear us, hopefully?
Yes.
Cool. Do we have any questions in the room, or anyone from online? You can speak up or go to the chat. Maybe I can start with one.
Yes.
So in your tables, you had kind of a number of different queries you might want to undertake. And actually, in one of the latest tables, I think that you had that some of the queries had like incompatible constraints on your inputs. Is that correct? So does that mean that for the same network or model that you can't have all the queries work all the time?
Do you mean this table, for example?
Yeah, so one of the earlier ones with the ticks.
Okay, something like this.
Well, yeah, exactly, yeah.
Yes, so for this, the way to read this table is that essentially you need, for example, to compute the power of the reals. So if I look at this column, you need three properties. You need smoothness, decomposability, and what's called here support decomposability or determinism. Yes. So how to make sure that your model has all the three? So you can either engineer the model by hand, or we have learning algorithms that, given a structure, can learn the weights of the model, or can even learn the structure of the model. So structural learning is a consolidated field in probabilistic machine learning and circuits. Yeah.
Cool, thank you. Any questions online, offline? Cool. Well, in the interest of time, I think we will thank Antonio and all the other speakers from today again.
Thank you.
And hopefully see you all in London, either in person or online.
Thank you. All right. Thank you all. See you.
Bye. Cheers.